Good afternoon, everyone. Today we are going to begin connecting the statistical tools we've been learning to Lean Six Sigma process improvement methodologies. Up to this point, we've discussed descriptive statistics, probability distributions, histograms, and variation primarily from a statistical perspective. Today we begin examining how organizations actually use these tools to improve real processes. The key idea I want you to remember throughout this lecture is: statistics are not just mathematical exercises. They are tools used to reduce defects, improve consistency, lower costs, and improve customer satisfaction. This lecture starts bridging the gap between statistical theory and industrial process improvement. In today's session, we will focus on several key concepts that form the foundation of quality and process improvement. You will learn why variation is such an important driver of quality outcomes, and how tools like the normal distribution help us understand defects and expected performance. We will also examine sigma levels as a way to quantify process capability and review the major components of the cost_per_ quality. Finally, you will gain a foundational understanding of process capability and see how all of these concepts connect within the DMAIC improvement framework. Lean Six Sigma brings together two major improvement philosophies. Lean focuses on reducing waste, improving flow, and eliminating non-value-added activities. Six Sigma focuses on reducing variation, reducing defects, and improving consistency. Together, they help organizations improve quality, efficiency, and customer satisfaction. Lean Six Sigma is used across manufacturing, healthcare, logistics, finance, and many other industries. Simple way to think about it is: Lean removes waste. Six Sigma reduces variation. Back in Module 1, we talked about DMAIC, the improvement framework at the heart of Lean Six Sigma. It walks us through 5 phases: define, measure, analyze, improve, and control. And if you've noticed, most of the statistical tools we've used so far really come into play during the measure phase and the analyze phase. That's where we dig into the data, figure out what's actually happening, and uncover the real drivers behind the process. One of the most important ideas in Six Sigma is that variation creates quality problems. Customers expect consistency. Even if the average output is correct, excessive variation can still create defects, rework, delays, warranty claims, and customer dissatisfaction. Statistical tools allow organizations to quantify and reduce variation. Real-world processes are affected by many different sources of variation. Some common sources include machine wear, operator differences, raw material variability, environmental conditions, and measurement system errors. One of the goals of Lean Six Sigma is identifying which sources of variation are causing the most problems. Some variation is normal. Other variation indicates a process problem that requires corrective action. This slide is really the bridge between statistical methods and Lean Six Sigma applications. Histograms help visualize process variation. Box plots help identify outliers and instability. Mean and standard deviation quantify process performance. Probability distributions help estimate defect probabilities. And Minitab provides the industrial software environment used to perform much of this analysis. The key idea is: statistics support data-driven process improvement. Now that we've identified the 4 primary pillars of our statistical toolkit, it's time to zoom in on our first line of defense: the histogram. While box plots and probability models give us mathematical depth, the histogram is where we first see process behavior in its raw, visual form. It is one of the most widely used graphical tools in process improvement because it reveals patterns that numbers alone can't show. Histograms help organizations visualize process spread, evaluate process center, detect skewness, and spot early signs of instability. In other words, a histogram gives us an immediate picture of how the process is behaving. For example, a narrow histogram typically signals good consistency. A wide histogram often indicates excessive variation that may require investigation. Because of this, histograms are a foundational tool in the measure phase of DMAIC, where teams work to understand the current state of the process before making improvements. Having examined how histograms allow us to visualize process behavior, specifically the spread, center, and overall stability of the data, we now turn to a foundational concept that helps us interpret those patterns more rigorously: Many real-world processes tend to follow a characteristic pattern known as the normal distribution. This distribution provides the statistical framework for estimating defect probabilities, evaluating process capability, and understanding natural variation. This is one of the foundations of Six Sigma analysis. If we understand the process mean and standard deviation, we can estimate how much of the process output falls within specifications. As seen in the lower image, approximately 68% of data fall within plus or minus 1 standard deviation. Approximately 95% fall within plus or minus 2 standard deviations, and approximately 99.7% fall within plus or minus 3 standard deviations. This is important because it directly relates variation to process consistency. Smaller standard deviation means tighter control, greater consistency, and fewer defects. One of the core goals of Six Sigma is reducing process variation. Sigma level is a way of measuring process capability and overall quality performance. As sigma level increases, a process produces fewer defects, shows better consistency, and delivers higher quality output. A true Six Sigma process corresponds to about 3.4 defects per million opportunities, an extremely high level of performance. Organizations use sigma levels to benchmark how well their operations perform and to identify where improvement is needed. From the chart, you can see how dramatically defect rates drop as sigma level increases. At lower sigma levels, defect rates are high and quality is inconsistent. At higher sigma levels, yields become extremely high and defects become rare. One important reminder: even a process with 99% yield can still produce a large number of defects when production volume is high. That's why Six Sigma organizations aggressively pursue variation reduction. Small improvements in variation can lead to massive reductions in defects. Now that we've introduced sigma levels and seen how they quantify process performance in terms of defects and yield, we can connect these metrics to their real organizational impact. A shift in sigma level is not merely a statistical improvement. It has direct consequences for operational cost, customer satisfaction, and long-term competitiveness. Sigma levels tell us how well a process performs, but the cost of poor quality explains why that performance matters. Poor quality generates significant operational and financial burdens. These appear in the form of scrap, rework, warranty claims, production delays, and ultimately customer dissatisfaction. A core principle in Lean Six Sigma is that variation and defects are expensive. As we saw in the sigma level chart, lower sigma levels produce far more defects, and those defects translate directly into higher costs. As sigma level increases, defect rates fall sharply, and the financial benefits are equally dramatic. Fewer defects, less waste, lower cost, stronger profitability. Even processes that appear good on paper, such as a 99% yield, can produce a substantial number of defects when volumes are high. This is why organizations aggressively pursue variation reduction and strive for higher sigma performance. We've just seen how the cost of poor quality are the direct financial consequences of variation and defects. The natural next question is, how do we evaluate whether a process is capable of avoiding those costs in the first place? That brings us to process capability. Process capability compares the natural variation of a process to its upper and lower specification limits. A capable process keeps its variation within those limits and consistently produces outputs that meet customer requirements. This slide highlights two essential comparisons: capable versus non-capable processes, centered versus off-centered processes. When the process spread stays inside the specification limits, defect rates remain low. But when variation becomes too large, or when the process shifts away from center, defects increase rapidly. A centered process provides more room within the limits and typically delivers stronger overall quality performance. Process capability analysis is a core Lean Six Sigma tool used to measure capability, analyze variation, improve processes, and deliver consistent quality. Later in the course, we will introduce numerical capability metrics, such as CP and CPK, that quantify how well a process fits within its specification limits. Six Sigma organizations pay close attention to process capability because it directly influences quality, consistency, and customer satisfaction. Now that we've established what process capability is and how it helps us evaluate whether a process can consistently meet specification limits, the next step is understanding how we actually perform these analyses in practice. In industry, capability studies, centering checks, and variation analysis are rarely done by hand. Organizations rely on statistical software to ensure accuracy, efficiency, and repeatability. This brings us to Minitab, one of the most widely used analytical tools in Lean Six Sigma. Minitab supports the full range of methods we've been discussing, from control charts and capability analysis to hypothesis testing, DOE, and regression. It automates complex calculations, reduces the risk of error, and provides clear visual outputs that help teams make data-driven decisions. To get a sense of how Lean Six Sigma works in a real industrial setting, consider a bottle manufacturing company that discovers a quality issue. Some bottle caps are too loose, while others are too tight. To understand the problem, the company begins collecting bottle cap torque data and analyzing the process using tools such as histograms, descriptive statistics, and defect probability analysis. These tools help the team visualize variation, estimate defect rates, and determine how the process is performing relative to customer specifications. The goal of this analysis is to understand how much variation exists in the process, estimate the probability of defects, and identify clear opportunities for process improvement. This mini-case study reflects how many Lean Six Sigma projects unfold in industry. Teams begin by measuring and analyzing the process using statistical tools, and then use those insights to guide engineering and operational improvements. Based on the analysis, possible improvement actions may include calibrating torque equipment, improving operator training, reducing machine variation, implementing process monitoring, and establishing control charts to maintain process stability. The expected result is lower variation, fewer defects, more consistent product quality, and ultimately higher customer satisfaction. One of the most important ideas in Lean Six Sigma is that statistics help identify and quantify process problems, while engineering and operational improvements solve them. In other words, data shows you where the problems are, and disciplined process improvement eliminates the causes. In the previous example, we focused mainly on reducing process variation and defects using statistical tools such as histograms, descriptive statistics, and probability analysis. That is the Six Sigma side of Lean Six Sigma. However, once an organization begins improving a process, it often discovers additional forms of waste that increase cost, slow production, and reduce efficiency. This is where lean principles become important. For example, in the bottle cap process, defects occur when caps are too loose or too tight, leading to scrap, rework, or customer complaints. Waiting may occur if machines break down or operators wait for adjustments. Overproduction could happen if defective bottles continue being produced before the problem is detected. Transportation waste may result from moving defective products to inspection or rework areas. Excess inventory can build up if defective products are stored while waiting for evaluation. Motion waste may occur when operators repeatedly adjust equipment or search for tools. Overprocessing can happen if extra inspections or repeated torque checks are required because the process is unstable. This demonstrates one of the central ideas of Lean Six Sigma. Six Sigma focuses on reducing variation and defects, while Lean focuses on eliminating waste and improving process flow. Together, they help organizations improve quality, reduce cost, increase efficiency, and deliver greater customer value. The key takeaway is that statistics are essential to Lean Six Sigma improvement. Reducing variation strengthens quality, consistency, efficiency, and customer satisfaction. DMAIC provides the structure. Minitab provides the analytics. And data-driven decisions lead to better operational performance. In the upcoming lectures, we'll continue building on these ideas as we move into process capability, control charts, hypothesis testing, and design of experiments. As we go forward, I want you to start thinking about real manufacturing processes, the operational variation they experience, the customer requirements they must meet, and how data can be used to improve process performance. The rest of the course builds directly on the concepts introduced today.